Welcome all. In this particular lecture, we are moving on to the bending stresses in beam, theory of simple bending, neutral axis, moment of resistance, and the assumptions for bending analysis, and the bending stresses in beams of various section, its strength, etc. So, what do you mean by bending stresses? Whenever a beam is subjected to an external loading, it may undergo a bending. The stresses developed due to that particular force which causes bending is known as bending stresses. So we'll see what are the things to be studied in this particular portion. So before that we are moving on to, I have already explained what is bending stresses. The resistance offered by the intended stress to bending. So the beam may bend whenever a load comes over it. So the stresses offered against that bending is known as bending stresses. Now the relevant theory related to that is known as theory of simple bending. We will just see what is this theory of simple bending. Before moving on to the theory, we have certain assumptions. There are mainly six assumptions to be considered before moving on to the theory. The first one is the material of the beam should be homogeneous and isotropic. Homogeneous means the bender beam should be made up of a same kind of material having same properties, and isotropic means equal elastic properties in all directions of the beams. So homogeneous and isotropic should be there. The material should be homogeneous and isotropic. Now the beam material should obey Hooke's law. So what is Hooke's law? Hooke's law states that stress is directly proportional to strain within the elastic limit of the object. So that law should be obeyed. The third one is the transverse section which were plane before bending remains plane after bending. That means if even if bending occurs, the bending should be uniform. Okay, that plane where the bending occurs should be plane before and after the bending. Okay, that's it. For example, if you are considering a wood is made up of a number of fibers, layers of fibers. So after bending, the layers of fibers may bend, but still it is plain. It should be plain. So that is one assumption. And the fourth assumption is each layer of the beam is free to expand or contract. Yes, the layers of the beam should expand or contract according to the bending. Otherwise it won't bend, right? Then the value of E, that is elastic moduli, is the same in tension as well as compression. That is another important assumption. And there is no resultant pull or push in the beam section. If there is some resultant occurs, if there is the existence of resultant, then it means that the beam may fail. So it shouldn't fail. Its resultant should be 0. That's it. So these are the assumptions to be considered before moving on to the theory of simple bending. Now what is this theory of simple bending? You can just see the um, figure here. So this is a figure showing a, this blue color shows the beam. So this is a beam. BDAC is a beam. Now when we are applying some load over the beam, so this distance is dx. Okay, the width of the beam is dx. Whenever we are applying a load over this particular part, we are applying a load over the beam, what will happen? The beam may bend. Okay, now AC was the top fiber, RS was the middle fiber, and BD was the bottommost fiber in this particular beam. After applying the load, the beam may bend, and the AC turns to A dash C dash, RS turns to R dash S dash, and BD turns to P dash D dash. But the thing is, while bending, what will happen? This topmost fiber will undergo compression because it should contract to form a bending, right? So A dash AC will convert to A dash C dash, which is smaller than AC, because that part will contract, while the extreme fiber, that is the outermost part, will expand. BD will convert to B dash D dash, which is greater than BD. So this part will expand and this part will contract, and from this point to this point the length will increase, the length of the beam will increase, this length will increase. Okay, at one point there will be one point at which that length will not change. For example, this RS, it is the center of the beam. So when bending occurs also, this RS will remain the same. R dash S dash will be equal to RS, because from contraction to expansion, that is from compression to tension, it will occur. At some point there is no compression, no tension. That particular point or that particular line is known as neutral axis. At this point no compression, neither compression nor tension occurs, above which compression occurs and below which tension occurs according to the loading. Got it? So here RS is equal to R dash S dash. But A dash C dash less than AC and B dash D dash greater than BD. So that is the thing. So here we can see the things. All the layers of the beam which were originally of the same length do not remain the same length. It will be on the same plane, but it won't remain in the same length. The length will increase or decrease according to the position of the layer. Got it? And the thing is, the top layer of the beam has suffered compression and reduced to A dash C dash. The layers in the lower layers have no doubt suffered compression, but to lesser degree, until we come across the layers RS. After RS, what will happen? It will undergo tension. RS has suffered no change in its length through bend into R dash S dash. The layers below RS have suffered tension, as a result of which the layers are stretched. Got it? Now, the layer RS, which is neither compressed nor stretched, is known as neutral layer or neutral plane. This particular theory is known as theory of simple bending. So whenever a beam bends, wherever the load is there, at that point compression occurs, and at the outermost layer tension occurs. At some point there will not be neither any compression or tension. That particular point is known as neutral plane or neutral layer. So this is known as theory of simple bending. Now what is this bending stresses? So we'll consider a small length of the beam dx, and m is the moment acting on the beam. Let m is the moment acting on the beam. Theta is the angle subtended at the center of the arc. So this beam will bend into this arc. Okay, now we are subtending an angle O. This particular angle is known as theta. This particular angle is theta. This is the radius r. This particular distance is r. R is, we are taking r dash s dash, which is the neutral layer. For example, we are taking neutral layer here. From a neutral layer to O, it is capital R. It is the distance. Let the layer, we are taking a small section from this particular part, that is PQ. PQ is within the compression zone. So this is the neutral layer, this is the compression zone, and this is the tension zone. So in the compression zone we are taking layer PQ. So here whenever a beam bends, it will compress to P dash Q dash. Got it? Now what is the decrease in length of P? Actually whenever compression occurs, whenever bending occurs, the layer PQ will compress. Okay, now the change in length of PQ will be equal to delta L is equal to PQ minus P dash Q dash. What is strain? Strain is nothing but it is change in length to original length. Change in length is PQ minus P dash Q dash divided by original length PQ. From the geometry of the curved beam, we find that the two sections O P dash Q dash and O R dash S dash are similar triangles. O P dash Q dash and O R dash S dash can be considered as similar triangles. By the principle of similar triangles, it can be written as P dash Q dash divided by R dash S dash. So this particular distance P dash Q dash divided by R dash S dash is equal to what is the distance of P dash Q dash? It is R minus Y. This distance is Y and this total distance is R. So R minus Y. From O it is R minus Y up to this point, and from O it is R up to this R dash S dash. R dash S dash like R P dash Q dash like R minus Y. So from the theory of similar triangles you will get it as R minus Y by R. So this can again be converted like this: P dash Q dash divided by R dash S dash is equal to R minus Y by R. When 1 is subtracted from both, when this value is subtracted from 1 on either side, we'll get it as this 1 minus this P dash Q dash divided by R dash S dash is equal to 1 minus R minus Y divided by R. So we are cross multiplying this, we'll get it like this. Okay, R minus Y, so R and R got cancelled, we'll get Y by R. So R dash S dash minus P dash Q dash divided by PQ. Now what is this R dash S dash? It is nothing but it is the neutral layer. So in the neutral layer what will happen? Its length will not change. So R dash S dash is equal to RS. RS is equal to PQ. PQ is equal to AC is equal to BD. So this RS can be equal to anything. So RS is equal to, we are providing R dash S dash as RS or PQ. We can provide it as PQ because it is equal to PQ. So PQ minus P dash Q dash divided by PQ is equal to Y by R, because R dash S dash is equal to RS is equal to PQ. Now what is this PQ minus P dash Q dash? It is nothing but it is the change in length. Change in length by original length, that is strain. Change in length by original length is strain. That is epsilon. Epsilon is equal to y by r. So I'll get this as one relation. The strain epsilon of a layer is proportional to the distance from neutral axis. Y is nothing but it is the distance from neutral axis to the fiber we are taking. So this is a neutral axis. P dash Q dash is the fiber we are taking. So this distance is y. So we can say that strain is proportional to that y. Moving on to the next part, bending stress sigma v is nothing but strain into all stress is equal to strain into elastic modulus. So here bending stress is equal to strain into elastic modulus. Strain is epsilon, elastic modulus is E. Epsilon is y by r. In the previous equation we have already derived that. So I'll get sigma b is equal to y into E by r. So the stress at any point is directly proportional to y. We can, from this equation we can say that stress is directly proportional to y. Okay, the above expression can be also written as sigma b y by is equal to E by r. So this is another relation. Earlier one was epsilon is equal to y by r. Otherwise sigma b y is equal to E by r. This is another relation. Now what is the position of this neutral axis? Where this neutral axis will be? Neutral axis is nothing but it is the line of intersection of the neutral layer with any normal cross section of the beam. It is known as neutral axis. Okay, it is the line of intersection of the neutral layer. Neutral layer means wherever there is no compression, no tension. That particular layer is known as neutral layer. Got it? So we are taking this particular figure. Na is the neutral axis here. We are assuming that Na is the neutral axis. We are taking a section, as in the earlier case we are taking a section PQ in the compression zone. Y is the distance from neutral axis to the compression zone. Delta A is the area of the layer PQ. And now here what is the intensity of stress? It is equal to y into E by r. We have already derived that. So total stress on the layer PQ is y into E by r into the total area of PQ, that is delta A. Now the total stress of the entire section is, we have to integrate it, or we have to find the sum of all the sections. Now we are taking only PQ. There are many number of sections here above this neutral axis, right? Here one section is there, here one section is there, here. So sum of all the areas of this section will give you the total stress. So total stress is nothing but it is sigma of y into E by r into delta A, which is equal to E by r we can take outside because it is a constant, into sigma y into dA. This is the total stress of this particular section. Now the for being the beam in equilibrium, for making the beam in equilibrium, the total stress should be 0, right? So that means E by r into sigma y into dou A will be equal to 0. We cannot make E by r 0 because it is constant. E and r should be constant. There will be some value for that. So we cannot make it 0. So that means sigma y into dou A is equal to 0. Either this or this should be 0. This couldn't be 0. So then this should be 0. Sigma y into dou A is equal to 0. So y into dou A is the moment of area about the neutral axis. Y is the distance and dou A is the area. Area into perpendicular distance will give you the moment of area. Sigma y into sigma dou A is nothing but it is a moment of entire area of the cross section above the neutral axis. So this y into dou A is nothing but it is the moment of area. So in this equation we have found that the moment of area should be 0. The moment of area should be 0 to make this particular beam in equilibrium. That means the neutral axis of a section will be so located that the moment of the entire area about the axis is 0. Now where is the moment of area 0? The moment of any area is 0 about an axis passing through its centroid. അതായത് മൊമെന്റ് ഓഫ് ദ ഏരിയ 0 ആണെങ്കിൽ മാത്രമാണ് ആ പോയിന്റിലാണ് ന്യൂട്രൽ ആക്സിസ് ലൈ ചെയ്യുന്നതെന്നാണ് പറയുന്നത്. ആ മൊമെന്റ് ഓഫ് ഏരിയ 0 ആവുന്നത് എവിടെയാണ്? ഇറ്റ് ഇസ് 0 ഓൺലി അറ്റ് ദ സെൻട്രോയിഡ്. സെൻട്രോയിഡിലാണ് 0 ആവുക. ദാറ്റ് മീൻസ് ന്യൂട്രൽ ആക്സിസ് ലൈസ് ഇൻ ദ സെൻട്രോയിഡ്, എ ലൈൻ പാസിംഗ് ത്രൂ ദ സെൻട്രോയിഡ് of the beam. So the location of the neutral axis is where it is located? It is located at a line or in a line passing through this centroid and normal to the plane of bending. That is it. So this line will be the neutral axis of the section. So we were finding the neutral axis, position of the neutral axis. It is nothing but the position should be along the line which is passing through the centroid and perpendicular to the force. Now we are moving on to another part, that is moment of resistance. The tensile and compressive stresses on either sides of the neutral axis will form a couple. How it forms a couple? So this is a neutral axis. Above this, compression occurs. Below this, tension occurs. So this particular thing should be in equilibrium, right? For making this into equilibrium, this force should compensate this force. That is, this force should be equal to this force. Compression is negative and tension is positive, right? So positive and negative, both are opposite in direction and both should be equal. So when two forces are opposite in direction and equal and opposite in direction, then that forms a couple. So we can say that the tensile and compressive stresses on either sides of the neutral axis will form a couple whose moment must be equal to the external moment. So the moment of this couple which resists the external force or external bending moment is known as moment of resistance. So then either side of the neutral axis, compression and tension occurs. They forms opposite forces and equal in magnitude. So it forms a couple. The moment of this particular couple which resists the bending moment is known as moment of resistance. Now how this moment of resistance we could find, that we will discuss. Stress, as we have said earlier, stress is equal to y into E by R. Now the total stress of the layer PQ is nothing but y into E by R into the area of PQ, that is delta A. Total stress of the entire section is nothing but, sorry, this is the total stress. Now the moment of this total stress, moment of the stress will be y into E by R into dou A, that is the stress, into perpendicular distance. Wherever moment comes, we know that we have to multiply it with perpendicular distance. So this is the stress. Moment of this total stress is nothing but this stress into y. So E by R into y square into dou A will give you the moment of the stress. Now the algebraic sum of all such moments about the neutral axis must be equal to m, that is the bending moment, total bending moment or total moment of resistance. M is equal to sigma of E by R y square dou A. The total moment of stress is nothing but it is sigma of this particular value. So sigma of that particular value will be equal to the total moment of resistance. So as we have said earlier, E by R is a constant, so we have to put this out. E by R into sigma y square into dou A, we will get it like this. Now this sigma y square into dou A represents the moment of inertia. You know what is moment of inertia? Moment of inertia is the second moment of area. Second moment of area. So y into dou A, that is the second moment of area. So that will give you the moment of inertia. So in the previous equation, here you have a term sigma y square dou A. Sigma y square dou A is nothing but it is moment of inertia which can be represented by the letter I. So we'll get it as m is equal to E by R into I. From that m by I is equal to E by R. So this is the second relation. In the previous equation, one of the previous slides, we have already derived that sigma by y is equal to E by R. So from that we can write m by I is equal to E by R is equal to sigma by y. This equation is known as the equation for theory of simple bending. So this equation is very much important in your syllabus. You have to study the derivation of this particular equation. So in the earlier case, we have derived it as sigma y is equal to E by R. In this case, while finding the moment of resistance, we have derived it as m by I is equal to E by R. From that, we will get three-termed equation. M by I is equal to E by R is equal to sigma by y. So this is the equation for theory of simple bending. Got it? Now we are moving on to the cross section of a beam. So this is the cross section of a beam, how the bending stresses are distributed. So we can say that this is the neutral axis and here compression occurs and here tension occurs. So we can say that at this point there is no compression, no tension. When we are coming from this point to the extreme fiber like this, the compression will increase and at this point the compression will be maximum. So here you can see this is the stress diagram. At this point the force will be 0. From this compression occurs, compression increases and maximum will be at the topmost fiber. Got it? Now from this point downwards if you are coming, the tension, it will be tension zone. The tension will increases and it will get maximum at this bottommost fiber. That means the maximum stress or either compressive or tensile takes place at the outermost fiber, at top or bottom, outermost fiber. Okay, at topmost fiber there will be maximum compression and the bottommost fiber there will be maximum tension. Now, in other words, while obtaining the maximum bending stresses at a section, the value of y is taken as maximum. What is y? Y is nothing but it is the distance from the neutral axis to any fiber. At this point, this point, this point, any point, it is y. So, when the y is maximum, at that point, the maximum stress will occur. So, when the y is maximum in the upward direction, then the maximum compression stress will occur. And when the y is maximum in the downward section from this point to this point, then maximum tensile stress occurs. Okay. Now, by the theory of simple bending, m by I is equal to sigma by y. From that, m is equal to sigma I by y. This I by y is nothing but it is z. Z is nothing but section modulus. Section modulus is the ratio of moment of inertia to the perpendicular distance. So, when y is maximum, so we have told in the previous equation that y should be maximum to get the maximum stress. So, we are providing y max. Sigma max will occur at I max and y max. So, you'll get it as sigma max into z. Z is nothing but section modulus. So, m is equal to sigma into z. Another equation you will get. Now, for finding the section modulus of different section, we are finding for rectangular section. What is section modulus? Section modulus is nothing but I by y. What is I? I for a rectangular section is nothing but it is BDQ by 12. Now, what is y? Y is, in the picture you can see, for a rectangular section, y is the neutral axis will lie at the center of the rectangle. This is not the case. The neutral axis will lie at the center of the rectangular. Now, what is y? Maximum y, it is the total. If the total depth is d, then y is nothing but it is d by 2. So, for a rectangle, y is nothing but d by 2. So, BDQ by 12 by d by 2 into 2 by d you can write. So, you will get it as BD square by 6. Section modulus of rectangular section is BD square by 6. Similarly, for circular section, I is pi by 64 d raised to 4 and y is d by 2 again. So, you will get it as pi by 32 d square. That is the modulus of section of a circular section. So, this is about modulus of section modulus. Now, the strength of a section. What is the strength of a section? It is otherwise known as flexural strength. The tensile or compressive strength which we get for a section of a beam is known as flexural strength. Now, it is indicated by the moment of resistance offered by it. Normally, M is moment of resistance which is equal to, which can be synonymously used as the strength of a section. So, M is sigma I by y is equal to sigma I z, which represents the strength of a section. The moment of resistance of a beam section does not depend upon its cross-sectional area. From this equation, it is clear that area is not a factor which depends on M, but area is depend upon y. But M is depend upon y. Y is nothing but the position from the neutral axis. Now, in a beam subjected to transverse loading, the bending stress at a point is directly proportional to its distance from the neutral axis. That is the important thing to be noted. And a larger area near the neutral axis of a beam is uneconomical. So, what the thing is, y is the maximum distance and the strength will be maximum at y. Okay, at a distance which is farther from the neutral axis. So, we can say that at y distance, wherever the strength is maximum, at that particular point we have to provide maximum quantity of material. ഓക്കെ, അതായത് ന്യൂട്രൽ ആക്സിസിൻ്റെ അടുത്ത് നിന്നും y ഡിസ്റ്റൻസിലാണ് സ്ട്രെങ്ത് കൂടുതൽ എന്നാണ് ഇവിടെ പറയുന്നത്. അപ്പോൾ ആ y വരെയുള്ള ഡിസ്റ്റൻസിൽ, അതായത് ന്യൂട്രൽ ആക്സിസിൻ്റെ തൊട്ടടുത്ത് മെറ്റീരിയൽ കൂടുതൽ കൊടുക്കുന്നതുകൊണ്ട് വലിയ കാര്യമില്ല. y ഡിസ്റ്റൻസിൻ്റെ അവിടെ മെറ്റീരിയൽ കൂടുതൽ കൊടുക്കാന്ന് വെച്ചാൽ ഇപ്പം നമ്മൾ ബീം ഉണ്ടാക്കുന്ന കോൺക്രീറ്റ് കൊണ്ടാണെങ്കിൽ ആ കോൺക്രീറ്റ് കൂടുതലായിട്ട് എവിടെ കൊടുക്കണം? y ഡിസ്റ്റൻസിലാണ്, ന്യൂട്രൽ ആക്സിസിൽ നിന്ന് കുറച്ച് അകന്ന ഒരു ഡിസ്റ്റൻസിലാണ് കൊടുക്കേണ്ടത്. അപ്പോഴാണ് സ്ട്രെങ്ത് കൂടുതൽ ഉണ്ടാവുക. ന്യൂട്രൽ ആക്സിസിൻ്റെ അടുത്ത് കൊടുത്താലും കുഴപ്പമില്ല, പക്ഷേ മെറ്റീരിയൽ കൂടുന്നതിനനുസരിച്ച് കോസ്റ്റ് ജാസ്തിയാവും, കോസ്റ്റ് കൂടുതലാവും. അപ്പോൾ ആ കോസ്റ്റ് കൂടുതലാവുന്നതും നമ്മൾ കൺസിഡർ ചെയ്യണമല്ലോ. സോ അവർ മെറ്റീരിയൽ അവർ ബീം ഷുഡ് ബി എക്കണോമിക്കൽ ആസ് വെൽ ആസ് സ്ട്രോങ് ഇനഫ്. So, for making that strong and economical both, we have to provide the material maximum at I point. That is, normally I section ആണ് നമ്മൾ കൺസിഡർ ചെയ്യുക. Providing beams of sections where the flanges along withstand almost all the bearing stresses. അപ്പോൾ I പോലൊരു സെക്ഷൻ നമ്മൾ കൺസിഡർ ചെയ്യാണ്. സെൻറ്ററിൽ ഒരു തിൻ സെക്ഷനും y ഡിസ്റ്റൻസിൽ ഒരു കൂടുതൽ മെറ്റീരിയലും കൊടുത്താൽ I sections are most economical sections, we can say. Now for symmetrical section, the bending stresses will be how the bending stresses will be changing. The neutral axis of a symmetrical section passes through its center. Maximum bending stress is at a section which is occur in the extreme fiber. As we have said earlier, സെൻറ്ററിലായിരിക്കും ന്യൂട്രൽ ആക്സിസ് ഉള്ളത്, എക്സ്ട്രീം ഫൈബറിലായിരിക്കും മാക്സിമം ബെൻഡിങ് സ്ട്രെസ് ഉണ്ടാവുക. സോ ആ സെക്ഷനിൽ ഇവിടെ ഇപ്പം റീഇൻഫോഴ്സ്മെൻറ്റ് കൊടുക്കുകയാണെങ്കിൽ വി ഹാവ് ടു പ്രൊവൈഡ് ഇറ്റ് ഹിയർ. ഇഫ് യു ആർ പ്രൊവൈഡിങ് ഹയർ എമൗണ്ട് ഓഫ് മെറ്റീരിയൽസ് ഓൾസോ വി ഹാവ് ടു പ്രൊവൈഡ് ഹിയർ. ദാറ്റ്സ് ഇറ്റ്. For unsymmetrical section, what do you mean by unsymmetrical section? So for example, rectangle is a symmetrical section. Okay, if there is a T section, then it is an unsymmetrical section. Then its y will change, right? For example, if I am drawing it like this, so this is a T section. Okay, now this is the neutral axis of a T section, for example. Okay, this is y, this is y1, that is, this is a compression zone. So the maximum distance to the extreme fiber is y1. Now from this to this it is y2. Okay, we have already told that the bending stresses will be maximum at the topmost fiber, or the most extreme fibers, either here or here. Okay, now where will be higher, either at the top fiber or the bottom fiber? For symmetrical section there is no problem. This y is at the center, this and this will be equal, this is also y, this is also y. So we can say that at both the point, at this point and this point, the bending stresses will be same and it will be maximum, we can say. But in this case we cannot say like that. So at that point, where the bending stresses will be maximum? Wherever y is maximum. For example, here the length of y is greater, so the bending stresses will be maximum at the topmost fiber. So this is how you have to find the maximum bending stress or the strength of a unsymmetrical section. So with this we can complete it. Thank you.